So let's draw an example. So I'm going to draw my lattice. The cross is the origin. And that's going to be my polygon. So we see the origin is an interior point. The vertices are all primitive lattice points. And well, what's the length of this edge? It's 4. The height is 1. So that condition is satisfied. And it's the same for this edge. And here, for these two edges, length and height are both 2. So the condition is also satisfied. And so why?
The length and height are in terms of the lattice.
In lattice length and height. Yes, correctly. Yeah. So why do we care about these T-polygons? Or in general, why do we care about Fano polygons? It's because under mirror symmetry, we expect them to correspond to Fano varieties. I mean, here we're in dimension 2, so we expect them to correspond to Del Petzl surfaces. So of course, we need to impose some kind of equivalence relation on these polygons. I'm going to tell you about this in a moment. But roughly, Fano polygons to some twiggle correspond to deformation families of Del Petzl surfaces. And in order to make this actually correct, I have to insert the word Q-Gorenstein here, but I don't want to talk about this. And so how do T-polygons enter the picture? We expect T-polygons to correspond to families where the generic member is smooth. So I guess deformation families of smooth Del Petzl surfaces. Of course, again, with this twiggle here. So, of course, we know how many deformation family of smooth Del Petzl surfaces there are. There's 10. So a good way to test this conjecture would be to see if there's also 10 T-polygons up to this equivalence relation. And so I'm going to tell you what this equivalence relation is. It's called mutation. Probably a few of you have heard this in various talks, and Al's going to talk about this as well tomorrow. So let me just briefly say what, in a picture, basically what it's supposed to be. So fix a polygon, I guess a Fano polygon P. Take the inward normal vector to an edge. N to an edge E of P, and take a line segment or a lattice segment F, which is orthogonal to N. Okay, so let's do this in, the picture's over there. So I need to do it again. Okay, so what about we take this edge here, then the inward normal vector is that thing here, and I'm going to take my lattice segment to be that. Okay? And so what I do is I remove minus k copies of F at height k when k is negative, and I add k copies of F at height k or k non-negative. So what I mean by height here, height measured with respect to this normal vector n. So that's the part of the polygon which is at height -1. That's the part of the polygon which is at height 0. And that's a part of the polygon which is at height 1. So how does it look like after I do the mutation? Got my lattice again. Okay, so I remove one segment of f here. I do nothing on this, on the height 0 bit, and I add f up the height 1 bit. So I get that polygon here. And so this process of doing mutation, obviously, I mean, as I've seen, I mean, it's not obvious at first, but turns out that if the two mutation equivalent polygons give you the same mirror del Pezzo surface, and also the property of T being a T polygon is preserved by this operation. So, and what I want to do is now to classify these T polygons up to mutation. It's already been done actually. So, so there is a combinatorial classification of those. To mutation. And surprise, there's exactly 10 mutation equivalence classes. And it's due to Al Kashbashik, Benjamin Mill, and Thomas Prince. So, and they, I mean, from the definitions, this is really kind of a combinatorial question. You're just doing combinatorial operations on a polygon. And that's what the proof also is doing, basically. It's a combinatorial proof. And as such, it is a bit hard to understand for a geometer. And also as a geometer, you always strive for a geometric and intuitive understanding of the world. And so we were kind of trying to see if there's a geometric way to prove this, also because this is related to mirror symmetry in such an intricate way. Also, yeah.
Is there some reason why you didn't add the vector in the other direction?
Yes, I mean, it is equivalent, yeah. So if you're being exact, you have to say, I write this edge as a Minkowski sum of that f and some other stuff, and then I remove the f, but it turns out to be equivalent. You can, yeah, you could have added it on the other side as well, yeah. So you want to add it here?
But you would have also subtracted it.
Yeah. Yeah. Yeah, I mean, but these turn out to be equivalent up to SL and Z or something. SL2Z. Yeah, something like this. Yes, and also a combinatorial proof like this is very hard to generalize to higher dimensions. You can play a similar story in dimension 3. We expect it to be true to some extent. But already here, it's quite hard. And in dimension 3, the combinatorics becomes completely intractable. Okay.
Well, you know, combinatorics is a resource for people. It's intractable to us. But,
I mean, the proof is already quite long, and yeah. So the first question is. So the question is sort of how do we associate a geometric object to these polygons? And as a toric geometer, that's something you do every day. You just take the normal fan of the polygon, and that gives you a toric variety. The only problem with that is that you sort of need to leave the world of toric varieties in order to do something mirror symmetric. So we need some additional thing, and that's going to be a Laurent polynomial. So need additional input of a Laurent polynomial f such that the Newton polygon of f is p. So just in case someone hasn't seen this, the Newton polygon of x plus 1 over xy is just you put x corresponds to this lattice point, y corresponds to that one, and 1 over xy is that one, and then you just take the convex hull. And of course, there's a lot of choice here. There's lots of Laurent polynomials which give you the same polygon, and I'm going to say something about it later, but now let's just take some Laurent polynomial, okay? So P gives a polarized toric surface XP dp, where dp is the divisor associated to the polygon. So for each, each edge of the divisor corresponds to, each edge of the polygon corresponds to a divisor, and you just take the multiplicity to be the height of that edge. And it's sort of well known from toric geometry that lattice points of P give a basis of sections for O of the divisor. But now we've got two sections in our picture, I claim, because we've got our Laurent polynomial, which is just a combination of lattice points of the polygon. And then on the other hand, we assumed that the origin is in the interior. So we've got another section just given by the monomial 1. Okay. So we have a pencil given by 1 and f on xp. And if I just draw a schematic picture, then the toric boundary of xp is the vanishing locus of 1, the section 1. And I'm going to draw the vanishing locus of f. I mean, there's really, I'm doing something a bit random here. So it's just some curve inside the toric variety, okay? And what the pencil is going to do, it's going to interpolate between these two curves. So the other members of the pencil are going to look like this, and so on. And we see immediately this pencil has base points, and they are all on the toric boundary. Yeah. So we blow up these base points. And we get a surface X, which comes with a map to P1. And what's the fiber of a point ST? It's just given by roughly a it's a compactification of the curve F equals S over T. Okay, so now, do we have anything else in this picture? We actually do. So we have this divisor we started with, the toric boundary, and we can look at the strict transform. So, I mean, it is always true that the toric boundary of a toric variety is an element of minus k. And so by construction, so if we only blow up points. So okay, let me say something and first write it. We only blow up points on the toric boundary. So the strict transform, which I'm going to call D, transform of the toric boundary. Is that clear? Maybe I should write it out. Transform is an element of minus kx. So this is not always true. So this uses that we're on a T-polygon now. Maybe I should say this. So P is a T-polygon now. And also you need some tiny constraints on your Laurent polynomial. Basically what you don't want is that you have some infinitely near base points, such that when you blow one, so you could imagine that all of the curves are actually tangent here. So if you blow up once, you actually haven't resolved the base locus. And the new base point that you get, you really want it to be on the strict transform of the toric boundary. And if you do something too general, this might not work. But in the situation that we are in, it actually turns out to always work. So all of the base points are actually either on the toric boundary or on the strict transform under some blow up. So actually we've gotten ourselves a pair XD, where X is a rational surface. D is an element of minus kx, and D is a nodal curve. So it's always nodal because the toric boundary is always nodal. And these things are commonly studied in mirror symmetry. They're called Leuenka pairs. Hope I pronounce this correctly. Michel isn't here to correct me anymore, so. Huh? Okay, maybe I should just call it anti-canonical pair to.
Get it wrong too, it's a Frisian name, so they don't know.
Yeah. So this is a Leuenka pair, or also called an anti-canonical pair. And so there's a fairly recent, I mean, not that recent, but kind of 10, 20 years old result, which gives a Torelli theorem for these Leuenka pairs. So and that, I guess, is due to some extent, Friedman and Leuenka himself. I think it was only proved recently in complete generality, and that was due to Gross, Hacking, and Kiel. Okay, let me move to that board. So to such a pair, we want to associate a period point, okay? So we have our pair XD. Can you see it right here? Yeah. And what I'm going to do is I'm going to define a lattice, the lattice lambda, which is a sublattice of the Picard lattice, and it consists of those line bundles which intersect every component of D trivially. So here, D is a sum, D is a cycle of -1 curves, or it might be a nodal curve, but so Di are just the components of D. And we're on a rational surface, so the Picard group H2 and the Néron-Severi group are all, everything's the same, so we don't need to worry about this. So this is really a lattice. And I'm going to define a map. So goes from the lattice lambda to pick 0 of the divisor. And it's actually very simple. I just take a line bundle and I just restrict it to D. And then because L was an element of the lattice, it meets every component trivially. So it has actually degree 0 on the whole divisor. And so, yeah.
Doesn't meet.
No, I mean, it meets it with self-intersection 0, with intersection C. Yeah, 0. So, yeah. Yeah, it doesn't meet the trivial, correct. Yeah, it meets it with intersection 0. Yeah, I mean, good point, Alyssa, because I'm going to draw a picture now. So,
I was going to ask you, can you draw a picture?
yes. So, as you see, I mean, how did we end up with this pair XD? We started with a toric surface and made a bunch of blowups on the toric boundary. And that's actually a very common way to generate these Leuenka pairs. So let's just take a toric surface, XP, and the boundary of XP. As I said before, the toric boundary is always anti-canonical. So we get to our Leuenka pair by just doing a bunch of blowups here. So I blow up once here, maybe, blow up once here. Maybe here I do 2 blowups, okay? Let me call these exceptional divisors E1, E2, E3, and E4. Yeah? So now we see that E1 minus E2 is an element of the lattice, right? Each of them meets it once, and so the difference meets it with intersection 0, and so is E4. So and what's the period point for those two things? Okay, so let me give these points names. So that's lambda 1, that's lambda 2, and that's lambda 3. So the period point of this, well, I just restrict E1 to that divisor, and that gives me O of lambda 1. And minus E2 gives me O of minus lambda 2. On the other hand, E4 really doesn't meet the divisor at all. So if we restrict that to the divisor, we just get O. So from this, we kind of see that the less generic the points are that you blow up, the larger the kernel of the period map, of the period point.
Sorry, what the lambda i's?
The lambda i's are just the points on the toric boundary that I blow up.
Okay.
So
Yeah.
this is a divisor, so you've written down divisor on the bound.
O lambda 1 is a divisor on the boundary. Yes.
So we have this thing which is an sort of an elliptic curve.
I mean, what is an elliptic curve?
That prime.
Yeah, if you want to. Yeah. Yes.
And one
It's a nodal elliptic curve. It's a cycle of rational curves. Yeah. Oh, sorry. I should have said. Yeah. This thing is isomorphic to C star. Yeah. So if you want to specify an isomorphism, you have to do some identifications.
Yeah, no,
But yeah, let's not get into the details of that. Yeah, but basically the idea is if you just blow up the same point over and over again, your period map is going to have a period point. It's going to have a very large kernel. So it kind of measures the genericity of the blow-ups in a way. So how does this help us with this? Okay, before I say that, so if we start with a T-polygon, and we take some F such that the Newton polygon is P, then under some mild conditions on F, so we have this, so we do this game where we have this pencil and we blow up at the base locus and we get a surface X with a map to P1. In this case, that's actually an elliptic surface. Surface X over P1. And D is a fiber of Kodaira type IN, which just means it's a cycle of n rational curves. So, and what we know about Kodaira's classification is that in any singular fiber of an elliptic surface, all the components have self-intersection -2. Yeah, so that of so that's one additional piece of data we have in our picture that isn't true in general. Okay, I realize now that I'm jumping a little bit because I haven't yet stated the Torelli theorem, but I'm going to do this now. So does it, I think it still fits on there. So Torelli for Lorentz pairs. So there's various ways of stating it, and I'm going to opt for the simplest possible one. So in a family of Lorentz pairs, period point determines the pair up to isomorphism. So if you want me to be a bit more precise, so suppose we have a family of pairs curly X, curly D over S. So each fiber is a Lorentz pairs and S is some smooth connected base probably. And we take some path in S. And we assume that the fiber over gamma of 0 is xd, fiber over 1 is x prime d prime. And because we're in a family, parallel transport gives us an isometry from the Picard group of x to the Picard group of x prime. So mu from pic x to pic x prime. And I think I barely have place for the punchline. So if phi x prime, doing phi x prime is the same thing as first doing mu and then doing phi x, then the two pairs are isomorphic. Okay. As pairs. Preserving, yes, preserving D. So that's what I mean by an isomorphism of pair, that under this isometry, each component of D is matched up with the corresponding component of D prime. Sorry? Did I not? Yes. Did I write something else? Where?
Oh, I'm very sorry.
Yeah, pick 0 is C star. Yeah. Sorry? Oh, thank you. So, and now the strategy is going to be, so remember that we started with a polygon and then we just chose some Laurent polynomial. Now we're going to use that freedom and choose a very specific Laurent polynomial such that we know what the period point is going to be. Okay? So now, if we choose a maximally mutable Laurent polynomial, I'm not going to define this. I'm just going to explain what it means in this picture. So let's take our good old T-polygon again. So to specify a Laurent polynomial, all I need to do is to assign a coefficient to each lattice point of the polygon. What I'm going to do is I put 0 at the origin, and I put binomial coefficients at the edge. Sorry, yeah, that's true. So that's 1, 4, 6, 4, 1, 2, 1, 4, 6, 4, 1, 2, 0. And it turns out these points are also determined. And in this case, they're just 8, which is 4 times 2. For T-polygons, there's always a, I really don't want to get into mutations because I was going to tell you all about that. But it turns out for T-polygons, this is essentially unique. And what's the point of doing it this way? So if you have binomial coefficients like that, turns out you can factorize your Laurent polynomial a lot, which means that instead of the curve f equals 0, doing something like this, actually, is that different chalk? Actually, it concentrates all of the vanishing to sort of one single point. So the Laurent polynomial here would meet the point here in a single point of multiplicity 4. Yeah. And here, for example, it would have an ordinary double point. So it would look something like this. And what does this tell us about the period point? We remember that I said the less generic the points you blow up, the larger the kernel. And it turns out that if you choose the coefficients like this, then actually the period point is just 1. The whole thing is in the kernel. So then,
But you're asserting this normal to that.
Sorry?
Yeah.
I mean, you've given us a nice example of a rectangle.
Yes, I mean, this works always. You can prove this.
for any T-polygon.
Yeah.
Okay.
Then, right. So I'm going to write XF. Well, XF is the surface associated to F as period point phi XF, just identity equal to 1. And now we're going to use the Torelli theorem. So the Torelli theorem said something like, if you're in a family of Lorentz pairs, then the period point determines the surface. So one thing you need to prove is how many deformation families of Lorentz pairs are there. At the moment, I'm trying to, I mean, ultimately I want to prove that every two, if you, so now I want to prove how many different deformation families of Lorentz pairs there are. Then I'm going to say my surfaces that I create have to be isomorphic to one of those reference surfaces in these families. Let me just write it down. I think it's going to get easier. So you can prove there are 10 deformation families of pairs XD such that D is a cycle of -2 curves. Okay, so there's 10 different families. Now I take, and in also the period map, I should have said, sorry. Every period point is realized by some Lorentz pairs in this family. So the period map is surjective. Every period is realized by some pair. So in particular, in each of the 10 families, I can pick some pair xi di, which has period point 1. Okay? Pick the unique pair xi di with period point phi xi equal to 1. And now by all, yeah.
Each family, does that mean we fixed the T-polygon?
No, we haven't. This doesn't mention T-polygons for the moment. That's a pure question about Lorentz pairs. You can prove there's 10 deformation families of such pairs, such that D is a cycle of -2 curves. And also, you know, the period map is surjective. So in each family, you can single out one pair, which is period point 1. And now enters the T-polygon. So I take any T-polygon P, I take my maximally mutable Laurent polynomial. This gives me a pair XD, such that these are a cycle of -2 curves, and such that the period point is 1. So it has to be isomorphic to one of these 10 reference pairs. Yeah? So any T-polygon P, this gives me a Laurent polynomial F. This gives me a surface XF D, where D is a cycle of -2 curves. And the period point is 1. And so it follows that XF, the pair XFD, is isomorphic to one of, sorry, XI, one of those reference pairs, DI, XI DIs.
Sorry, so when you say the period point is 1, is this like, is it stuff you're not saying like why that's true? Like, should that obviously be 1?
I mean, I didn't give a proof, of course, but the idea is that if you choose the coefficients like this, the vanishing locus of F becomes very non-generic. So you get points of very high multiplicity and points, sorry, very high tangency or very high multiplicity. And if you were to resolve the base locus of the pencil, here you would have to blow up, I think, 4 times until you resolve it. And then all of these curves here are going to be in the kernel.
The polynomial restricted to that line is T1 minus T2 to the power 4.
Yeah, exactly. Yeah, that's exactly the point. So what we've done so far is we've taken any T-polygon, and this cookery that we did, we showed that it gives us a surface which is isomorphic to one of the 10 reference surfaces. Okay. And now we're going to relate this back to the original question of classifying these polygons up to mutations. Okay.
Well, the existence of the 10 definitions there on line 3, that's input from other theories.
That, yeah, sorry. So that requires some maths, this statement here. Is that what you mean?
Yeah.
That's because we've already solved the problem.
Well, I mean, the story about this is a bit interesting because Friedman has this paper on the geometry of anticanonical pairs where he claims the results and provides a sketch proof. But in my opinion, there's at least 5 pages missing from that sketch proof. And so I spent a few months sort of proving this actually works. So there is some non-trivial mathematics to do this. And in threefold, that's going to be easier than classifying polynomials. Yeah. I mean, we don't really know which strategy is going to be the best one, but thank you very much. Yeah. So actually, one last thing I want to say, each of these 10 reference pairs, they all actually arise from some fixed T-polygon. So I can get each of those 10 pairs by starting with a T-polygon, taking the maximally immutable Laurent polynomial and blowing up some stuff. So these arise from polygons Pi with Laurent polynomials Fi, or let me call them Gi. Yeah. Now I have the following picture. So I have my T polygon P. And I get my surface XP, and I blow up to get XF.
So I guess maybe at this point you don't worry about running back. You have a T-polygon P.
Yeah.
And you want to show that it's mutation equivalent to one of those 10 polygons.
Yes, exactly.
That's the goal at this point.
Yeah.
That's the end.
The punchline. Yeah. So I have my T polygon P, and I want to show its mutation equivalent to one of the PIs. So what did I do? I started with XP, blow up some stuff to get my surface XF. I know this is isomorphic to XI, and XI just arose from blowing up some stuff on XPI. So inside both of them, I have a torus, because these are just toric variety. So all of these maps are birational, so I can just go all the way over, and I get a birational map from C star squared to C star squared. And so what does this map satisfy? Claim that if you pull back the Laurent polynomial Gi, which was the maximally mutable associated to Pi, you get F. And that is basically because you remember that these surfaces came with a morphism to P1, and if you restrict it to the torus, it just gives you the Laurent polynomial back. And you can sort of arrange for this isomorphism to preserve that fibration. I mean, it already preserves one fiber, and then you do some arguing. But essentially, it means that everything, the fibration is preserved. So one Laurent polynomial puts back to the other one. And another thing which is true is that this birational map is volume preserving. And this is true because you've only blown up points on the boundary of the toric variety, and never blown up in the interior. And so now the point is that we want to show That's the final thing, and that's the thing that I haven't finished yet. That this map, this birational map, which satisfies these two things, decomposes into some smaller maps. So need to show that phi is a composition of phi1, phi n, such that the pullback of, now I need to get my indices right, I is fi minus 1, I guess fn is g, and f0 is f, gi. In other words, I want to decompose it into simpler maps, such that at each simpler birational maps, so these are birational mutations. I was going to say this, yes, sorry. I wanted to sort of say that first. So if you pull back by a generic birational map, you won't get a Laurent polynomial in general. So that's already a condition. But you also want these maps to be something which are called mutations. So at the beginning, I told you about mutations of polygons, and I didn't tell you about mutations as birational maps. It's basically a very similar concept. A mutation is a birational. Maybe I should just write it down if you give me 2 more minutes. So we take n, a primitive lattice vector. Let's just forget about lattices and work in Z2. And I define a birational map from the torus to the torus by sending a monomial. So u is in z squared. Send that to x to the u times 1 plus x to the v inner product u and n, where v is orthogonal to n. So it's something very similar to what we did on polygons. So this measures kind of the height of the monomial relative to n. And this thing here, this monomial, if you take the Newton polygon of that, that's just this line segment that we had before, which was orthogonal to the normal vector. And so if you split out your Laurent polynomial in parts that are at height -1, at the part that is at height 0, at 1, then this tells you the part at -1, well, you need to divide by this Laurent polynomial here. The part at height 0, you don't do anything. And the part at height 1, you multiply with this factor. From this, it's actually pretty clear that if, for such a mutation, phi I pull back fi, so if fi pulls back to fi minus 1, then this induces a mutation on the Newton polygons. It depends. You could take it. You could take it as a definition. There is some, yeah. So I think there's this thing that not every mutation of polygon arises, or was it the other?
No, you do have to worry about left and right, because V is in n part, and you have to choose one of those two.
Yeah, for example, you could also add a scalar here or something. So, I mean, that's basically the punchline now. Sorry if you've missed it. But we've taken our map phi here. We've decomposed it into smaller pieces like this. And we assume that each step, when we pull back, we get another Laurent polynomial. And we've shown that on Newton polygons, we get a mutation from the Newton polygon of F0 to the Newton polygon of F1 up to the Newton polygon of Fn, which is Gi. So didn't have space for the punchline. So P, which was the Newton polygon of F, is mutation equivalent to Pi. which was the Newton polygon of GI. And that kind of, if you believe me, this decomposition, which I still need to show, and which basically involves some birational geometry. Maybe I should comment on this briefly. So there is something is known about this. Actually, let me just keep it like this. So if you have a volume preserving birational map like this, then Jérémy Blanc showed that it decomposes as a composition of maps like this. Yeah, but that's not strong enough for what we want, because we also want that the Laurent polynomials pull back at every step. And if you want a Laurent polynomial to be mutable, so if you want the Laurent polynomial to pull back along this, to another Laurent polynomial along this birational map, you kind of need the normal vector to align, to be perpendicular to an edge of the polygon, right? And Jérémy Blanc just tells you it's a composition of some mutations for some ends. And these ends just might not be one of the normal vectors of the edges. So we need to do something a bit cleverer, and we're working on it, I guess. So thank you for listening.